So in the previous videos, we've looked at a half-wave rectifier, which is essentially only able to rectify the voltage in the AC voltage into a DC voltage for half of the wave, as the name suggests, but they're hardly ever used in practice. So there's a couple of issues, and we can discuss those as we go along. But the main thing is that you have well, one of the main things was that you only have half of the wave being rectified, and during the other half of the time of the period, you're not really rectifying anything. In addition to that, there's a sort of high ratio of AC source volt amps to DC power, basically meaning that the AC source operates at a low power factor, which creates a DC component in the AC source's current. So you have an AC source that has to supply a DC component, which is not a good thing, right? And so this creates problems for transformers in the source network and requires large filtering networks to eliminate such components. So the only real advantage of the half-wave rectifier is that it has a single diode drop, right? So I mean, the half-wave circuit, if you recall, looks something like this. So you have, this is the simplest case, this is not considering any inductors, that's a resistor, by the way. So the half-wave circuit looks something like this. So there's one diode drop between the AC and the DC side. Now this used to be beneficial, as I've mentioned in a previous video, when we used to have, back in the days when we used to have vacuum tubes, because in a vacuum tube, the drop here, this VD, or VAK, I think we called it in a previous video, this VAK drop, it was anywhere in the order of 10 to hundreds of volts in vacuum tubes. But the issue is, if you have multiple tens of multiple hundreds of volts of voltage drops across the diode, you only want to have one of them, or as few of them as possible. So you don't want to have any elaborate sort of topologies. But nowadays we have silicon, and so in silicon we know that this voltage drop is usually around 0.6, 0.7. You can even get sometimes as low as 0.3 or 0.2 volt drops in certain types of diodes. So this is no longer a concern for us. So what we do instead is we use what's called a full wave rectifier. Now you have probably seen a full wave rectifier as well if you've taken an introductory electronics course. But basically a full wave rectifier will connect the AC to the DC in both cycles. So let's take a look at what the full wave rectifier looks like. And sometimes this is called the bridge rectifier as well, because it forms what's called a diode bridge. But again, the name you give to it is irrelevant. So it looks something like this. So you're going to connect the AC source here between this terminal and this terminal. And so if you've seen the video on the full bridge DC-DC converter, this looks very similar to that. And in practice, you can actually use the two interchangeably, depending on how you control the switches in the circuit. But again, this is not a video on that, so we won't really get into that. So this is going to be VS, I'll call it because I'm running out of space there, but it's a sinusoidal voltage, right? So we're going to say this is a sinusoidal voltage. And I'm going to have a resistor here because, again, we're going to consider the simplest case here, and then we'll build on top of it later. So that's that. I will call this one here ID1, and then we'll call this here ID2, okay? And so these are two currents. And well, I mean, the diodes can also be labeled D1, D2, D3, D4. So if this top left is 1, this is 2, we can call this bottom one 3 and 4. For now, I mean, we're not really going to discuss those details, although I guess it might be useful too, so maybe let's do that too. So let's call this D2, let's call this D3, and let's call this D4. Okay, so what happens in this case? In this case, unfortunately, I don't have waveforms that are pre-drawn, but thankfully these are not very difficult to draw as it is, so we can do them freehand because these waveforms behave fairly nicely, let's say. So what happens here? So we're going to look at VD. Okay, so the first thing here will be VD. So this is VD. So what happens to VD? And what is VD? I guess that's more important to label on the waveform here. VD is this voltage here. And I've run out of space again, so maybe we remove this a little higher up and put ID2 like that, okay? So VD is the output voltage of the rectifier, okay? And obviously VD is going to follow VS, and so if VS is a waveform that is a sinusoidal waveform, then you know that VD will do this for the positive half cycle, okay? And then we know that VS would actually go down like this, but, so work through conduction states here now, if you're not familiar with how this thing works. So when Vs is positive, D1 is going to be turned on, and then D4 is going to be turned on. So the path between the AC and the DC side will do something like this. It'll go through here, it'll come down through here, and it'll go like this. Okay? So that's the path for this conduction state. And so what happens in this case is D1 and D4 turn on, and they produce a positive voltage across VD. Okay? Just because of the way that they're connected. Now, in the other case, when Vs goes negative, what's going to happen is the conduction path is going to go like this. So it's going to go down through D3, right? It's going to go across like this. It's going to go through D2, and then it's going to come back up like this. Okay, and the way that this is connected, the Vs source is now connected to VD in a reverse polarity manner. And what that does is that produces another positive cycle like this. And this should be sinusoidal, so if it doesn't look sinusoidal, that's my artistic skills that are lacking. And so this here should be pi, and this should be 2 pi. Okay, and that would continue. I mean, obviously, if it continued from 0 to pi, it should go from 2 pi to 3 pi as well, like this. And the amplitude of this, obviously, will be Vs. Okay? Okay, so that's Vs. Now, what happens to ID1 and what happens to ID2? So, ID1 and ID4 are going to be the same, while ID2 and ID3 are going to be the same. Okay, so ID1, let's say, ID1 is this one. And remember, D1 and D4 conduct during the positive half cycle of what would be the sine wave. So that means it conducts here, and it conducts here. And when it's not conducting, it's 0, obviously. So a non-conducting diode carries no current. And so it should be something like this. It should be a square wave. Okay? And the amplitude of this is obviously going to be Vs divided by R, right? So this is going to be Vs over R because this is a resistive load here. And so we can obviously look at the other current as well if we want to. So when D1 is conducting, D2 cannot be conducting, so it has to be 0. This has to be positive here, and so on, like this. Okay, and this is also going to be Vs over R. So that's what you have for this for the waveforms for this circuit here. This is a full wave, sometimes also referred to as the full bridge rectifier. And so what's the average output voltage? So the average voltage here you can see is going to be larger than it is in the half wave case. So the average voltage will be something in the middle, obviously, as we've drawn in the past. We can call this VD like this. And so we can find this average. So we can find this average VD by saying 1 over pi. This is now 1 over pi. In the previous case, it was 1 over 2 pi. The reason it's 1 over pi now is because this is now periodic with pi and not 2 pi anymore. So we're going to integrate this from 0 to pi and then divide it by pi, because that's the period. So it's going to be 0 to pi, and this will be Vs sine omega t d omega t, and this ends up being equal to 2 Vs over pi. And this is now twice what the half-wave rectifier was, which makes sense logically speaking, because we now have twice the output voltage, right? So in the other case, we only had half of the wave. Here we have the full wave, which is full is obviously twice of half. And so then we obviously expect the output average to be consistent with that too, which is true here, which is nice. So this is a more commonly used rectifier circuit. You'll see this in many electronics applications. I mean, if you open up any power supplies that are connected to mains voltages, you'll almost always, and by almost always I mean basically always, see a rectifier connected to a transformer of some type. So like this will be the terminals of a transformer, and the purpose of that would be to step down the voltage to some value that is comfortable for the rectifier to operate on. So if this is 120 volts mains connection, let's say, you might step it down by a factor of 10 so that it's a 12 volt signal here. So a 12 volt voltage is much easier for diodes to be rated for than 120 volts, for instance, and then you can deal with everything afterwards. So this is the standard sort of bridge rectifier case. But we can also have a case where we have, as we've seen for the other, as we've seen for the half-wave rectifier, we've seen the sort of commutation case, right? And why don't we then look at what commutation inductances do to the full bridge rectifier? And for some reason this little label doesn't really want to go away. There we go. So if you have a commutation inductance, you have a source voltage, obviously. Commutation inductance goes here, that connects there, that connects there. And then the output, again, we're going to model this as being a current source, because I don't really care what the current or what the load network is. I just care that I have some constant current there. And again, this is D1, D2, D3, D4. We can call this LC, and this is again going to be VS. And again, I didn't give myself enough space, but maybe we draw that in there so you know it's a sinusoidal voltage. And obviously the output voltage here is VD, so that's between there and there, right? Right. So again, for this case, what I'm going to do is I'm going to have to cheat, because these waveforms, there's no way I could draw these by hand, although the other ones were simple. This one is not. So there's a few more details to make sure of here. So here's what's happening here, right? So you have VS is obviously this, VS sine omega t. And then IS, I guess IS is what we're calling here the source. IS is this, right? So you end up having positive and negative current in this case. So it goes both ways. You can have positive and negative IS, because VS can obviously be positive and negative. And so what happens is the direction of the current can be reversed in a case like this, and it's allowed to be reversed because there are 4 diodes in this case. So in a negative cycle, you can reverse the direction of current flow. And obviously we see that this is VS and this is ID being this maximum load current here. And we see that there's this, again, there's this ramp up and there's this ramp down. So if you haven't seen the video on the commutation in the half-wave rectifiers, I'll link that in the description below so you can take a look at how we explained all that. But essentially what's happening in this case is the current is commutating between the different branches. So when ID is commutating from D1 to D2, for instance, it's also commutating from D3 to D4, or it's D4 to D3, because we have this sort of pairwise operation, right? So this one and this one conduct the same current, and then this one and this one conduct the same current, right? So because of this inductor, you can't have an instantaneous change, so you have a sort of a slow ramp-wise, or it's not even a ramp, it's more like a cosine looking thing. And so that change that happens is essentially the period, or the part of the period where this current is going from one branch into the other. And that causes a zero voltage, because what's happening during that is you have multiple conduction, multiple diodes. So you have diodes in two arms. They call, or sorry, legs. They call these 2 legs. So this is a leg 1, let's say, and this is leg 2. So you have D1 and D2 could be conducting at the same time, because the current's going from one of them to the other one. And therefore, VD will end up being 0 in those kind of cases, right? And so that's why you have this duration where from this time to here, U that they're calling it here in this waveform, U is this commutation period. And as you see in this waveform for the current, U is the time that it takes to get from the negative to the positive amplitude. And so you see the same thing here, right? And during this time, again, you have 0 here. So this is the commutation period, right? So the commutation period is essentially when the current's going between one branch and the other, right? So you can treat this kind of like 2 half bridges. So I mean, half bridges are just 2 diodes connected in series, and they're center tapped, sort of. And so that's what this is, right? But it's sort of like they're sort of in the opposite direction in terms of conduction. So when there's no commutation, the voltage drop across the commutation inductor is 0, since there's a constant current. And that's what's happening during this time, right? So there's no voltage drop across the inductor during that time. And again, you can go through and you can determine the commutation period. And we did this in the half-wave rectifier video. And so you just have to go through and you can write an expression for this. You can find out what it is. You can model it based on a sinusoidal voltage applied to an inductor. And so if you do that, you'll get that the commutation period in this case, U, is equal to the inverse cosine of 1 minus 2xcid over Vs. And so if you're confused about how to get this, what you can do is you can find out what the inductor current is. You find out the inductor current, so we call that Is as a function of omega t, will equal, let's say we're going to take this time here. Okay, so at this time, pi, we know that there's some current, so we're going to say Is pi plus, what's the voltage applied to the inductor? The voltage applied to the inductor is Vs sine omega t. So we're going to integrate this between pi and some generic time omega t, so we can get a function for what that thing is. This will be Vs sine omega t divided by the reactance of the inductor, which will be omega Lc, and this will be d omega t. Well, technically, it's mathematically incorrect to integrate that way, so we'll have to use tau as a placeholder, because you can't integrate from 0 to x of x or x dx, right? That doesn't make sense. So to avoid that, we use tau. And if you solve this integral and you know that Is of pi is equal to Id, because Id is this constant current here, right? So if this current here is Id, you can substitute it in there and you can get an expression for the entire thing. Then you know, on the other hand, here, you know another condition, so you know that Is of pi plus U is equal to minus Id. Once you get this overall expression, you can apply this condition that I've just shown here, this condition here, and then you can get this expression for U. So, what does that do for us after? So the commutation periods are equal, we know, and the commutation periods are equal because the current goes between positive and negative IDC, right? So what that means is that delta ID, or delta, this change in current, whatever current you have that's changing in this inductor, is going to be the same in both directions. Whereas in a half bridge, it only goes between 0 and IDC, right? So this current goes down to negative IDC, whereas in the half bridge case, this current stops at 0 and then goes to 0 and then goes back up again. So in a case like this, you expect that the commutation periods will be the exact same. And so the next thing we can do is we can find this average voltage, and to do that, we say 1 over pi, because it's periodic with pi, and it goes from U to pi, and this is going to be, again, Vs sine omega t, d omega t, and if you solve this, you get Vs, well, you get 2Vs over pi, and I'm making some simplifications here. This will be 1 plus, I guess you can say 1 plus cos, and let's just jump right into it. So let's go right into it, and we can say this is going to be 1 minus xcid over Vs. Okay, and so xc is the reactance of this inductor, so that's omega L, omega Lc is basically what xc is equal to, so that's the reactance here. And so we look at this, we see that when the reactance is not there, so if this reactance is 0, this is 2Vs over pi, which is exactly what the standard case of the bridge rectifier is, right? That's what this output is. So we see that as, or well, not even as, the effect of xc is it reduces the output average voltage, and it makes the whole rectifier operate such that its output voltage is now dependent on its output current. And we call this a load regulation characteristic, because the output current impacts the output voltage. It's just a definition. We call it load regulation, basically. How much does the output current impact the output voltage? Usually we want the outputs, we want them to be independent of one another. So that we want to be able to control them separately so that we can ensure some level of stability. But that may not always be the case, as we're seeing here. And as we're seeing here, if we compare this with, so this is for the full wave, and then in the half wave case, so in the half wave case, we saw that this, if we say half wave, So in the half wave case, and again, this is from the half wave video. If you haven't seen it, I'll link it below. So in the half wave case, we had this was Vs over pi 1 minus XCID over 2 Vs. So we have basically that the full wave case is twice the half wave regulation, which is not good, because what this means is that the full wave, well, I mean, it's not that it's not good, it's just it's not, I mean, it's one downside to the full wave, if there is any, because essentially what happens is the output current and output voltage are related in a more stronger type of relationship here. So the variations in the output current will impact the full wave more than they'll impact the half wave. That's literally the only benefit, but usually that trade-off isn't worth using a half wave rectifier. So we live with that, because we can usually ensure that the output variations are kept to a minimal, and so we don't really have any issues. So we often call this thing VD0, so whatever that term is, right? And so if that's VD0, then, well, they can't both be VD0, can they? So VD0 is going to be this one. So that one's VD0. And what we're going to do is we're going to plot this. VD average over VD0, right? So here it's a maximum, 1. And as XCID over VS increases, you have 1 here, and you're going to have 2 here. Probably just use the line tool here, which I always forget about, so let's use that, why don't we? So that is going to go between here and here. So that's that one, and then let's use a different color for the other one and do that. Okay, so there's 2 of them. And this is what's showing you, it's showing you the load regulation. So this one is the full wave, and this one is half wave with freewheeling diode. So we see that the full wave drops to 0 much quicker than the half wave with freewheeling diode. And we said that this term was basically it acts as a resistance, although it's not a resistance. You can kind of view it as being a load resistance, because it acts so as to further decrease the load voltage as the load current increases. So we see here that the full wave has this downside, but overall we've discussed the issues with the half wave quite extensively at this point, but it's not worth the sort of trade-off that we see between the two. So it's always a good idea to use a full wave. It's almost never used anymore. Like the half wave is almost never used, despite the fact that this thing exists here. Okay, so in this video we looked at the full bridge, and the full bridge is a fairly straightforward and very useful and very common circuit. And so we saw that the average output voltage is twice that of the half wave, and then we looked at the commutation characteristics, and we saw that it behaves kind of similar, but there's also some differences. The main difference being that IS can go negative as well, whereas in the half wave case it doesn't. We also saw that the overall expression is similar, but there's also a main difference, which is this sort of factor of 2. So the half wave is twice as good in terms of this condition, but this condition in itself is not sufficient to convince us that the half wave is better than the full wave across the board. So I hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.